Hello everybody, this is Sebastian Böcker from the Friedrich Schiller Universität Jena in Germany, and this is a talk about SIRIUS and ZODIAC. You might have already seen our software, SIRIUS 4. It's actually a wrapper software which wraps all of our other software as well. So through SIRIUS you also have access to CSI Finger ID. It has a nice and shiny user interface, and probably you want to know how to use it, but sorry, this is not what this talk is about. Instead, what I'm going to do here is I'm trying to explain how SIRIUS works, how ZODIAC works, why we did things in this way and not in another way, and so on and so on. So if you want to learn something about using our software, we'll have separate talks for that, how to do that, tutorials and so on, but this is not what this talk is about. So this is currently the full Monty of our software, or more precisely of our scientific approaches. We much prefer the word approach, scientific approach, for these things, because this is really, at some stage also software, but this is really the very last thing that we do, that we have to program something which people can use. But before that, we have to develop something that, solves the problem. And just the software development is basically not that complicated. But coming up with something like SIRIUS, that is rather involved. And I'm going to try to explain you what we did there. And because it's so much, and I don't want to put all of that into one single lecture, I'll just talk about SIRIUS and ZODIAC in this one, and I'll do another one for CSI Finger ID, and then probably more for Canopus and Cosmic. So before we start, a few words. I assume that if you're listening to this talk, you already know that metabolites are important, natural products, they can be biomarkers, and so on and so on. We want to find new drugs, we want to know something about drug abuse or drug use, and there are millions of reasons why you want to study metabolites and other small molecules. By the way, this slide is stolen from a talk by David Wishart. So kudos and blames to him. So if you want to do metabolomics or small molecule research, you have two choices of instrumentation. One is nucleic magnetic resonance. And if you want a full de novo structural elucidation of a small molecule, you need 2D NMR. There's probably no way around that. But I'm not going to talk about NMR because mass spectrometry has one huge advantage, and that's its sensitivity. I'm not talking about general mass spectrometry here, and I don't want to get into details here. I just want to say that we are just considering high resolution, high mass accuracy data. And for us, that means it has at least 10 ppm mass accuracy. And I usually assume that the mass spectrometer has been coupled to a liquid chromatography, and that we do tandem mass spectrometry in the next step. So tandem mass spectrometry, by the way, on the slides you will also see MS, and I won't use MS2 probably, but I use that interchangeably. I noticed that some chemists think that there are differences. I don't know. This just makes it complicated. Let's not make it that complicated. So tandem mass spectrometry, and I assume it's DDA, data-dependent acquisition, fragments a single molecule, and then you try to learn something about the molecule, identify it in the best case by looking at the masses of the fragments. We know that it's highly reproducible. We know that compared to what could happen combinatorially, not too much peaks show up in the spectrum. Sometimes not enough peaks show up. That's actually worse. But we also know that it's pretty hard, even if you know what the structure is, to predict what the spectrum is. And I mean for a reasonably sized metabolite like 500 Dalton or something. It's even pretty hard to explain, if you know the structure and you have the spectrum, what happened. Yeah, there are still new fragmentation reactions discovered every now and then. So we are there still somewhere, I don't know, at the beginning, I would even say. So what people have been doing is spectral library searching. So you measure some large library of reference standards, usually commercial stuff that you buy, and then you check if your spectrum looks similar like one of those, and if it does, then you hopefully have identified a metabolite. This has been done in GCMS for literally decades now, many decades. So it's not really a new idea, and it's not really a very deep idea or surprising idea. And it obviously has the drawbacks that you can only identify where you can previously actually record such a commercial reference. And we know that for a lot of these things, we actually don't know what is identified. Anyways, let's wrap up. We consider small molecules of biological interest. I sometimes call them biomolecules, just to have another short word. I already heard that some chemists now have a problem with that word. I just use it as an abbreviation for everything that might be of biological interest, might come up in such a experiment. We use LCMS, we use tandem mass spectrometry, we use high mass accuracy. High resolution is not that important, but the mass accuracy should be 10 ppm or better. The better the mass accuracy, the better our results get, the faster our algorithms run. Everything gets better with higher mass accuracy, by the way. Okay, what I show you is for something like 10 ppm data. We only consider data-dependent acquisition, so no DIA, where we also have to deconvolute the spectra first. And I have to tell you that all of that is what SIRIUS and ZODIAC and our other tools offer out of the box. We can also process other data, for example, MSN data. We are not limited to tandem mass spectrometry data, but this is what is implemented currently in SIRIUS as it can be downloaded from our webpage. If you want something else, worse mass accuracy, maybe even go into the direction of DIA or something, we would have to cooperate. There is no ready software for that. So let's consider a specific task for this talk, and the task is very simple, and it should be one of the first things that you do when you analyze a molecule, and that is we want to know the molecular formula of the molecule. And we will consider this task de novo, that is, we will not look up the molecular formulas from some structure database. Instead, let's consider them all. Why? There are different ways of telling you why this is a good idea. Let's go first from the application side. When you restrict yourself to molecular formulas from some structure database, then with every new version of the database, more structures are added, and with that, more molecular formulas are added. But if you would have said that HMDB 3.0 contains all the molecular formulas which are of interest to you, you would have missed all the molecular formulas that are new in this part of the database. Okay? But now you have HMDB 4.0, so everything is good. No, obviously not. There will be a next release of HMDB, and it will contain more structures and it will contain more molecular formulas. So I find it a little bit worrying that if you would redo your same analysis, with same parameters, same software, everything, suddenly you will discover completely different molecular formulas simply because there are now more candidates. Okay? Do you then rewrite the papers, or I don't know. I don't like the idea, I have to say. It's not only of theoretical interest. Here are two novel molecular formulas that we found in the diatoms dataset by looking de novo. Okay, they look pretty complicated, but yeah, there will be also simple molecular formulas which are novel. Obviously, yeah, if the more you limit your elements, obviously also again the easier the task gets. But we'll see in a second that even then it's not completely trivial. If you completely insist on not doing it de novo, then we don't insist. Okay, you can just consider molecular formulas from a structure database. And actually, I have to tell you, and I'll show you a slide in a second that explains why, when you restrict yourself to the molecular formulas from some database, then all evaluation results will look much, much better than those which I'm going to show you. That is because it makes your task easier, and with that, all approaches get better. You won't be able to find novel molecular formulas. Maybe you don't care, and that's okay. Maybe you want to search in a structure database afterwards anyways, and then you don't need novel molecular formulas. But that's the other explanation why I will look at that part of the problem. It's the more challenging problem. And as I will repeatedly tell you, it's better to evaluate methods on a challenging problem and see whether they can solve that than trying to evaluate them on some super simple problem and then find out later that the method actually didn't do anything. It was just, the problem was so simple that every method would have solved it. So that's the computer scientist or bioinformatician's answer to that. Okay, we will always evaluate on something that is complicated. And just to demonstrate to you how much easier it gets to find molecular formulas in a database or de novo, you might know the game, this search pictures where you actually have to search for Wally. So you tell me, where's Wally in this picture? Obviously he's here and he's here, but that's not the point. Where is he in this picture? Can you see him? I can't, even though I have done this repeatedly and I always forget where he is. Sorry. So let's compare this with this instance of the problem. Another instance, I should do that. Where's Wally in the right picture? Can you spot him for me? Oh, it's not that hard. I think here he is, right? Okay, that was easier. I still can't spot him here, even though that we now know that we have to search for this. See, maybe here. No, it doesn't look like it, right? But there should be right there. My goodness, I can't even see that he's there. Anyways, that's more or less the comparison between considering all molecular formulas and considering molecular formulas from some database, from some rather large database, by the way. It just gets easier, okay? So please, whenever you see an evaluation that somebody says, I can identify molecular formulas with this identification rate, please look up if this person is considering this problem or that problem. Because if he's considering that problem and he won't get like 99 point something %, then his method is probably completely useless. But even if he's getting it 99.9% right, I mean, okay, spotting Wally here is really so easy. What does that mean? So let's go for the de novo problem. Short teaser. For a paper, we recently had to also evaluate other methods. Here you see SIRIUS. This is ZODIAC, the green one. This is, by the way, the error rate, like how many molecular formula annotations are wrong for a complete data set. And then you see, and that's the only thing that I wanted to show you here, that both SIRIUS and ZODIAC are much better than all other methods here. Like there's the only reasonable competitor probably is GenForm. Sometimes it's also the 7 golden rules. Exact mass, even if restricted to a tiny alphabet of elements, CHNO, gets something between 30% and 90% errors. Gets even worse if you add more elements. I mean, 90% of the compounds that we evaluate on are made from CHNO, so you usually gain again if you restrict the alphabet a little bit further. But anyways, this is different league. I mean, the only data set where SIRIUS and ZODIAC don't work well is the mice tool data set. And this is, in a way, a horrible data set. Contains loads and loads of chimeric spectra where I'm not even sure if the ground truth that we have there is a ground truth or something different. And now you might say, oh my God, but we are still losing this and this many molecular formulas. Yes, this is the way that you have to look at it. This is the reality. I mean, you can hide this fact by simply searching in a molecular structure database and then never seeing what you are doing wrong, okay? And in evaluation, you won't see that you're doing something wrong because all evaluated compounds are in the databases. But this is the current standings. And obviously, if somebody now gives me 1 ppm data, everything gets better, okay? This is not 1 ppm data, so we are happy to get that. The fact that high mass accuracy alone and the mass of the monoisotopic peak alone is not sufficient to find the molecular formula, or as Kind and Fien call it here, the elemental composition, is not new. This is a 2006 paper. It has, I think, more than 600 citations, so everybody should know it. Yeah, and it already says in the title what it's about. Mass accuracy is insufficient at 1 ppm. Yeah, so that's not new and everybody should be aware of that. But let's now talk about SIRIUS. And SIRIUS has many different facets. As I already told you, it's a wrapper app for all the other things that we do. I'm not going to talk about that. It has a shiny graphical user interface. I'm not going to talk about that. It now does data processing, LC-MS, MS processing. Very cool. Has a lot of advantages over previous versions which had to integrate the data from other tools. I'm not going to talk about that. It also incorporates now feature detection and adduct assignment and so on and so on. I'm not going to talk about that. That should be also a separate talk at some stage. What I'm all going to talk about are these 2 points. And first, let's talk about isotope pattern analysis. And the basic idea behind identifying the molecular formula with an isotope pattern has been described in the 2006 paper by Kind and Fien 2. It's more or less a small figure where everything is contained in that. Funny fact, in the very same year we published our paper that describes an approach that solves exactly that problem. So for all these different steps, there were solutions in there. Another funny fact, whereas the left paper has 600 citations, I think this one has 30 or something. It's a little bit extreme, but okay. I mean, people then rather tend to cite the software papers, not the ones that describe the solution. Let's zoom in. This is more or less the approach that is implemented in our software, and for every software. I mean, it's not that complicated. It's always the same. What you first do is you take the monoisotopic peak here. Then you use what Kind and Fien called a molecular formula generator, what we usually call the decomposition approach. And with that, you generate a list of molecular formulas that all agree with the monoisotopic mass that you have seen in your experimental spectrum. You do some chemical filtering out molecular formulas which cannot be real. And then you compare the isotope pattern that was seen experimentally with the isotope pattern that you simulate for each of these candidates. And whereas Kind and Fien call that a filter, everybody implements that in truth as a scoring. So how good do these agree? And then you rank by the score of the agreement. This part, by the way, is then more or less, the future, okay? Has nothing to do with the molecular formula identification. Let's first focus on the molecular formula generator, or as I said, as we call it, the decomposition. It's quite easy to come up with a very naive solution, or actually there are two naive solutions, and we have seen them millions and millions of times, and you have probably seen them. I mean, you just nest for loops. For each element, you make a for loop, and then you iterate over all of them. That has a huge bunch of issues. I mean, simply try out to do that with let's say, 10 different elements or 12 different elements and go to mass 1200 for me, or maybe 1800. How about that? Yeah. I mean, with a very modern instrument with, say, 0.1 ppm, 100 ppb data, that might be possible. Simply see how long it takes just to compute the decompositions for that. Faster is a database approach where you generate all molecular formulas, calculate their masses, and then you sort them, and then it's a very quick lookup in the database to find all the decompositions for one given mass. Unfortunately, this uses huge amounts of memory for this rather tiny step of the analysis. I mean, this is what we will do as soon as we analyze Tandem MS data again and again and again for every peak. So that shouldn't use much memory and should be fast nevertheless. And this is now a very efficient and elegant solution, and it's solved once and for all. Not really once and for all, because there's one more paper, but it's done more or less. The algorithm is there. It has very nice properties. For example, the input mass is not part of the running time anymore. That is, as long as you have few decompositions, you can also decompose masses at 5,600 Daltons. Okay, if at some stage we are at 1 ppb instruments, no problem. This algorithm will quickly give you an answer. In fact, initially the algorithm was not even targeted at metabolites. It was a little bit, we had a solution and we were in search of a problem. I come from the world of DNA mass spectrometry. There it's almost overkill because the nested for loops, 4 nested for loops do the trick for you and rather quickly, so it makes it a little bit faster, but not much. The other, back then, seemingly good application were peptides, amino acids, but you see that the problem then explodes. The number of decompositions simply gets extremely high very quickly. Yeah, decompositions in millions. So you can do it efficiently with this algorithm, but what do you do then with a billion of solution or something? And the molecular formulas were the ones that looked best. So that's when we started actually thinking about that more. And as I told you, it's not totally true that this is a once and for all solution, because even if you have a best algorithm in a way, yeah, that solves the problem for all instances, you can still do a little bit of algorithm engineering. Okay, this is about algorithm engineering. Do we see that somehow here? No. Anyways, yeah, algorithm engineering there. we were able to make it a little bit faster in practice, which is like 10 times faster. So the algorithm was already extremely fast. I mean, I don't look at some weirdo input here with random masses or something. I really look at metabolite masses, and there we get it 10 times faster. And that's okay, and we happily take that. And it took a lot of work again on algorithmics to make it faster. This is not about computer programming. This is really making the algorithm better, or not better. So it still runs in the same class, complexity class, but yeah, in practice you get a little bit faster. After the decomposition of the monoisotopic mass, we have the simple problem of simulating an isotope pattern for it. And that is not really complicated. There was a paper by Rockwood and by my group in the same year that described how to do that. What both of us wanted was that we also have the isotope peaks wobbling a little bit to the left and the right, because that's what you actually observe. And we use, and Rockwood used, the weighted average of the isotopologues that belong to this +1, or in this case +2 peaks, as the mass. And that's pretty simple if you have finally completely understand it. Took us a little bit time. I mean, the computations are not really complicated, but the maths behind it then boils down to one very long equation that proves that this is working. It's very long, it's a full page, but that's all. One equation is usually not very complicated in math terms. Anyways, intensities, everybody should have seen how you can actually simulate those intensities. It's not very complicated. And with that, you can now simulate an isotope pattern. Now, the funny thing is that you have to compare those two, and that seems like an easy problem, but it's not. We had two different approaches, or not we, I mean we as a field. And one was ours, which is implemented in SIRIUS since 2009. And then Tomasz Kluszkal instead suggested that we use something that we just look at the differences, at the absolute differences, and sum them up, yeah, which is somehow the easiest thing you can come up with. Ours was much more complicated. And it's really true that the absolute differences often work better, and we were not happy with our approach, but the other approach was also not perfect. Somehow we were never really happy with that. Since 2009 we have been thinking about that again and again and again, and we never came up with something better until 2019. And now this might look complicated. This is the complete scoring in a way. Yeah, it might look complicated, but it's not. I mean, these are all constants. Here's 1, not constant, that's the x. But this is a factor anyways, which is not really needed. We would need only this one. And this is a very simple equation. And in fact, when you implement that in SIRIUS, it changes more or less one line of code. Okay, maybe 2, 3, 4, 5, because you calculate different things separately, but that's it. Getting to that equation was a little bit harder. Takes a little bit of mathematics. But it's not, again, not really complicated in mathematics. It's a little bit about distributions and so on. It's the normal distribution, and we have to make a maximum likelihood estimate, and so on and so on. But as I said, took us a little time to come up with it. And was that worth it? As I said, we changed one line of code and voila. It was extremely worth it. I'll show these slides again and again. I hope you have seen them before with other people or in other papers. It tells you how often you get the right answer at the first position of your output. I mean, as I said, we rank the different molecular formulas now, and hopefully the correct answer is now the top ranked. It's like a Google search. Google doesn't give you one web page, it gives you a ton of web pages, and hopefully the correct web pages are at the beginning of this list. Okay? And this now reports that the old scoring, SIRIUS up to version 3, gets the correct molecular formula, gives you back the correct molecular formula at the top position of the list in about 35%. And then just by changing this one line of code, SIRIUS 4 now gives you the correct answer in something like 62% of the cases. That's a dramatic increase for changing one line of code. And the point is, this change of code is not like, yeah, we try to improve the identification rate, and so we played around, and after 10 years we have found a change that improves results for one data set. Then you would never know if it also works for the next data set. But this is not the case here. What we have done is we've done mathematical considerations, very standard stuff like, which we know will always work, like maximum likelihood. Okay, that always gives you good results, and so on and so on. So very, very standard approach. It then took some time to actually get the equation solved. But after that, we built this in and checked how good this works. And it turns out that it works perfectly. And that tells us that it will also work for all other data sets. Okay, no matter what data you will throw at it in the next 10, 20 years, it doesn't matter, it will always perform very, very well. Okay, this is only the top position, and here we tell you how often we get the right answer at either the first position or the second position. That's why these curves always increase, because this is first position only, this is first or second, this is first, second, or third, and so on and so on. That's like, how often do you get the correct answer on the first page of Google results? That would be the top 10. I think they give back 10 results. Okay? And now you might say, oh, but I don't want to look at 10 different molecular formulas. Yeah, but a computer can easily do that. I mean, this is interesting also for the downstream analysis, and we'll see in a second that by combining it, for example, with Tandem MS data, results improve beyond this. Okay, with that I want to stop talking about the isotope pattern part, and I'll come to the second part, which is the fragmentation tree computation part. And the fragmentation tree computation part in principle tries to exactly do that. It tries to compute a fragmentation tree given a tandem mass spectrum. To explain a little bit more in detail what we are doing, I first have to explain what a fragmentation tree is. So it's computed from a tandem mass spectrum. I mentioned that we can also compute it from other data, MSN data, but that's not part of SIRIUS. If you want to do that, we would have to talk. What we need is high mass accuracy data, 10 ppm or better. And the important points here are, during the computation of the fragmentation tree, there is no spectral library, there's no structure database, nothing. Okay, there's no structure. We only consider molecular formulas. No structure of fragments, no structure of the whole thing. That's simply not known. It's no way to deduce that at that point. Because, as I said, we don't use a structure database or a spectral library. We would have to do de novo structural elucidation. That would be wonderful. Wow. But no, we can't do magic. So what a fragmentation tree then does is it explains the spectrum that we see here. So this peak has the same color as this node for a reason, because this node explains this peak. So the mass of this molecular formula, or the corresponding ion, if this is not the ion form, anyways, the mass of this is the mass of this peak plus minus the mass inaccuracy that we allowed. And that's true for any of these colored peaks in here. They are all explained by some node of this fragmentation tree. This is called a node. So it fits the mass of a peak, and each peak has at most one explanation in this tree. So you'll never see that this peak, purple peak, shows up multiple times in the fragmentation tree. At most one peak explaining it. There are some peaks which don't have an explanation. These are considered to be noise peaks. In the extreme case, we would give you back an empty tree just consisting of a root. We always explain the precursor, and then everything else would be noise peaks. That's an okay fragmentation tree. It is permitted. It would often obviously be a very bad explanation of what we see, but it's okay. What about this requirement that we don't explain a peak twice? That means more or less that we assume that each peak corresponds to a fragment with a single molecular formula. There might be different fragments with the same molecular formula. We are not talking about structure anyways, but we always say there's only one molecular formula explaining this peak. In practice, there might be super rare cases where you see a compound fragmenting in such a way that this peak might be explained by two different fragments which have almost indistinguishable mass, and they are both present at the same time. I have to say that I've never seen anything like that. It's so super rare. You'll have to search through hundreds or thousands of spectra to actually see that. If you could even then identify it, that this really happened and it's not only one peak. You would have to do it with super high mass accuracy and lower mass accuracy. And I would say this is so rare that we can really safely ignore that. Okay? Even if it would be happening more often, it wouldn't be such a big problem as long as we know that the fragmentation tree cannot cover that part of the tandem mass spectrum. Okay, but this is not the case. Here it's so super rare, we won't even notice it. Yeah, as I already said, we explained. So the other thing that you see inside this tree are edges. Edges connect nodes. That's how it's defined in graph theory and mathematics. And these edges correspond to fragmentation events. And you actually see the fragmentation part, the loss, which didn't ionize, and so you can't see it inside the mass spectrometry instrument, that fell off here. And you see, if you compare that molecular formula and that molecular formula, they are differing by an H2. So we have that for all the losses here. All the edges are annotated by the loss molecular formula, and it's again a molecular formula. It's not a structure. We have no idea about the structure. Now comes the important part. We assume that every node in this tree has exactly one parent, except for the root, which doesn't have a parent. So this one comes from here, and this one comes from here, and this one comes from here. And we know that for every fragment where it came from, every node, every molecular formula here. Okay? And the important thing is that it cannot come from this side and from this side simultaneously. That's not allowed in a tree. That's the mathematical object which is called in graph theory a tree, or actually it's called something even more complicated. It's an aberrance, but let's stick with tree, that's easier. And there the justification is a little bit harder, because we often see that one fragment can come from two other positions. Okay, here's just the loss again. And what you often see are these what we call parallelograms. Parallelogram means that two pretty common losses like H2O and CO2 either happen H2O first and then CO2, or CO2 first and then H2O. And both things happen. And we can't cover that in the fragmentation tree. In the fragmentation tree, what you would see is that, for example, this loss is missing. It really depends then on the scores. So one of them would be missing, it would connect the other ones. So the fragments would be still annotated with molecular formulas, and hopefully the correct molecular formulas here, but you are missing one fragmentation reaction that is happening. Now, this is pretty easy to reinsert after we have computed the fragmentation tree. We have to forbid it during the computation. I'm not going into the details, but otherwise the whole problem doesn't make sense anymore. You won't get any results. We have to forbid them during the computation, but after we have computed them, you can easily reinsert them. We do that. I think the software currently doesn't have an option for that. It should have at some stage, okay? But you can also do it manually. It's super simple to see these things, okay? And if it's in there, there's an alternative explanation and you can manually draw in an extra edge. This might also happen on a larger scale, even more complicated and harder to track. But then it again gets, the arguments get against statistics tells us if something is rare, then we can safely ignore it. It's like if you take away 1% of your population, you are still able to look at the average of the mean of the population height or something. Yeah. So if something happens only in, 1% of the fragmentation trees, again, it's not as nice as in the previous case where I would really argue that it never happens, but I would argue here that even though this is not always the case, it's super easy to correct it in 99% of the cases where it did something wrong. Anyways, we have now defined what the fragmentation tree is. This is the summary of that. We want to annotate the tandem mass spectrum. We annotate the peaks with molecular formulas. And we tell you for each peak what is its parent peak. Where does it come from? Where does the fragment come from? This also tells us the molecular formula of all the losses. And the fragmentation tree, as I said, will not explain everything in here. Everything that is not explained is considered to be noise. So that was a complete wrap-up about fragmentation trees, I hope. Just remember, no structures, just molecular formulas and annotations of what you see in the spectrum. No database involved. Now the point is that the tandem mass spectrum, except for the noise, can be recovered from the fragmentation tree. The fragmentation tree contains at least as much information as the tandem mass spectrum. Obviously, we also record the intensity of the peaks here. But it contains more. Where does this additional information come from? And what additional information do we have? We sometimes have more than one molecular formula that explains this peak. So which one is the one that we put into the fragmentation tree? Random? Smallest mass deviation? Not really. Okay. In particular, there are usually many different routes for the tree. This is again the problem that we had initially. We decomposed this precursor, and then we have many molecular formulas, and for each of these molecular formulas we get such a tree. Or currently we don't even know how to get it, but let's assume we had one. But which one is then the right explanation as a molecular formula? And which peaks do we ignore? And the solution that we use for that is again a super successful solution from statistics. It's called maximum a posteriori estimation. Sometimes you use maximum likelihood, which is very nice because you don't integrate any background information into your model. But here we need a little bit of background information, which is not part of the data. For example, we put in some information about that there is a hotspot for losses. Losses, if you look through fragmentation spectra, losses often have a mass around 60 Dalton. And then the very large losses get fewer and fewer, also because there are fewer and fewer precursors which actually have this mass. Okay. Something that you can derive from the data is you see that the mass deviation is roughly normal, has roughly a normal distribution. Okay, so the difference, mass deviation between the peak mass and the molecular formula explaining it. Yeah. These two things now allow us to score each fragmentation tree, and with that to rank the fragmentation trees. We now know which tree is better than which other, because we assign a posterior probability to it, and then we say the one with the higher posterior probability is the better tree. And our task is to find the best one. Now, let's look at one more prior information which we have integrated. There's really very few things that we have integrated. We have a loss mass distribution, we have 2 or 3 other distributions, that's in total something like 8 parameters that we use. And then we have 2 tables, one is with common losses, one is with common fragments. The common loss table is more interesting. And it is based on the observation that certain losses simply appear much more often than they should, like water. Yeah, what else do we have here? They all have a name. The funny thing is that we found some losses which appear very frequently that no expert told us about, like hydrogen cyanide and methyl esters. We worked together previously with experts, and that is here ABC, and that is if some experts had pointed out that this should appear rather frequently. So for those, we didn't have that information. This is now derived completely from data. For those who know a little bit about statistics and statistical algorithms, it's an expectation maximization-like approach where we first start with some initial idea of how we could compute fragmentation trees. Then we do that, find optimal fragmentation trees, and then we count. We extract from that information what are the common losses in there and how often are they in there. Okay, and then we restart everything and hopefully it converges, and it did converge after a few rounds. Anyways, this is information that is derived from some thousand tandem mass spectra, and it's then used to score other fragmentation trees. But this is the only information where we ever looked at tandem mass spectra before, okay? And besides, except for this list and this other list and the few parameters, nothing remains from the spectral libraries that we looked at for that. Now, initially, we didn't have such a, smart, intricate, complicated, whatever scoring. Initially, we just came up with some ad hoc scores where we said, oh, if it's on the list of common fragments, then it gets +4. Why +4? Because 4 is somehow a nice number, sounded nice, and so we took that. That was all, and that already worked quite okay. And in 2016, this time it took 8 years, we redid everything, and now it's this maximum a posteriori scoring with all the statistics derived from data. But we still have the problem that we don't know how to find the best tree, and that's what I already mentioned earlier. We know if there is a tree, if you write up a fragmentation tree and it's admissible for the data, I could now, with all the stuff that is described in here, I can now compute the posterior probability of this tree given the data. And if it's high, it's good. If it's low, it's not good. But what is high and what is low? I mean, this obviously depends on the data. If you give it very crappy data, then the probabilities will be low. We want to find the tree that best explains what we see. And that's not solved. And that's a nice combinatorial problem. Again, we started rather from this nice combinatorial problem than from the statistics or from the data side. What we do is we transform the input tandem mass spectrum into a graph. Now, not a tree, a graph, a directed graph. It's a DAG, it's a directed acyclic graph, by the way. And if we have multiple explanations of a peak, we put them all into the graph, and they get the same color. So the peaks, as indicated in these drawings anyways, show you the color of this thing, and then We connect everything that is combinatorial possible. So if we can go from here to there via a loss, then we do so. We insert an edge, but we can't go from here to here. We would have to gain 2 hydrogen. That's not possible. We have to gain nitrogen. That's not possible. Yeah. Then we put all the information from the maximum a posteriori approach onto the edges of this graph, so that a maximum subtree in here is, or subtree in here always has the posterior probability that we would also derive for this tree if we would compute it via the a posteriori approach that I just showed you. What we then do is we search for a subtree of maximum weight, but it has to be colorful. And the point is, as I explained, we only want one explanation for every single fragment peak in here. Okay? It shouldn't have multiple ones. And why we did that back then was simply from an algorithmic or combinatorial point. If you would not do that, then the best solution is always take everything. Hooray, you've done it. Take everything. Take all the different explanations. They will always increase your probabilities, so it makes things better. Or take nothing. That would also be possible. But just trivial solutions. So we came up with this colorful requirement, and it turned out that this problem is NP-hard. And if you don't know what NP-hard problems are, I can only tell you to look it up in the internet. There's probably, you will probably find 10,000 web pages and 5,000 talks which explain that to you. You'll find something on YouTube and. It's one of the very big problems in theoretical computer science. It's open. What some people assume, or the majority assumes, is as soon as such a problem is NP-hard, which you can prove, we have proven that it's NP-hard, it will be NP-hard today, tomorrow, and in 10 billion years. If you can prove that your problem is NP-hard, then you won't find an algorithm with polynomial running time. Polynomial running time is like something like, if n is the size of your input, say n peaks, you n to the 2 or n to the 3 cubic, that would be polynomial running time. And what I just said is that you won't find any such algorithm no matter how high you set the exponent. So you won't find an algorithm which solves the problem in n to the 1 billion. Okay? It's not completely clear if this is the case. That's the big P equals or not equals NP problem from computer science, and you can make a lot of money by solving that one. But let's not go into the details anymore. So in principle, a few years, let's say 15 years ago, 20 years ago in bioinformatics, that would have been the point where people stop and start doing heuristics. You can't solve it anyways, the problem, can't find the best fragmentation tree. Let's find a good one. Maybe it's good enough. So what do you do when you don't want to compute just a hopefully good solution without any guarantees? So if you really want to go for the optimal solution, but nevertheless you have an NP-hard problem to solve. Now luckily some developments in algorithmics make it possible to still do that. When we started off, we did something which is called parameterized complexity, parameterized algorithmics. It has a problem that, running time and memory increase rather substantially with the number of peaks, exponentially to be precise, but not with the number of explanations. That was the big advantage of this approach. So it was relatively fast in practice, but it couldn't compute all the peaks. So what we did was we simply took the 10, 12 most intense peaks in the spectrum and computed this thing. Whereas the new approaches that I present here now really consider up to 50 peaks. So that's the big change. Anyways, we switched to integer linear programming with the next paper. That's actually a very well-known technique. We simply didn't see that it was possible here. Integer linear programming is a huge market where you can actually buy programs that then solve these so-called integer linear programs, and they cost you, I don't know, $50,000 per year. But there are also free alternatives, and one of those is now built into SIRIUS, and that's the reason why it's so fast. We are very thankful for those people who provide them for free. Here's another algorithm engineering paper on the topic, and that makes a pre-processing. It removes parts of the graph, the fragmentation graph, where never an optimal fragmentation tree could be present in there. So we can simply cut them off and the solution will still be optimal. And as always, if you make a problem smaller, it gets easier to solve. It also uses some ILP tricks, some advanced ILP stuff, such as facet-defining equations. And with that, I think the running time in practical instances was again brought down by a factor of 10. But the reason why the new version of SIRIUS, SIRIUS 4 and up from there are so fast is that we went back to heuristics. We noticed that to find the molecular formula, we don't really need the best fragmentation tree. The only thing that we need is that the correct molecular formula gives the corresponding fragmentation tree the best score. And Tim White came up with some very nice heuristics, which compute excellent fragmentation trees already. They look very often very similar to the exact solution, and they are totally okay to come up with the molecular formula of the whole thing. And then only for the supposedly correct molecular formula, we have then to compute the correct fragmentation tree with these other methods. And this speeded up the whole thing by a factor of, I don't know, in total maybe 1 million, 10 million, 100 million, I don't even know. As I said, this initial thing can only be run with relatively few peaks. You wouldn't notice that because we then reinserted the remaining peaks heuristically in the end, but with a not so smart heuristic as this one. And that sounds like a good idea, but I'll show you in a second that it wasn't. It was really good that we went all this way to this paper finally. A problem for evaluating the fragmentation tree is that we usually don't have the ground truth. I'll come back to that in 2 or 3 slides. But what we can do is we can rank trees and with that molecular formulas, and we do that on reference data. Our method doesn't know that this is reference data. Our method doesn't know what the correct solution is, obviously. Okay? And then we can see how often our method is capable of finding the correct molecular formula for the precursor. What we do is, for every molecular formula, we compute a tree, the best tree for that molecular formula. And then we rank those trees by the score, the maximum, the posterior probability, Okay. And then we can check if we got the correct molecular formula at the top position, in the top 2 positions, and so on and so on. Now, I'm usually very much against using prior information, and I'll probably make a separate talk why I don't like meta scores. Okay? But here, this is not a big problem because the prior information has never been used so that we could identify more molecular formulas correctly. It has never been used. We didn't even talk about that up to this point. Okay, it's completely independently. All the parameters of the model, and not too many. I mean, there are the parameters of the parameterized distributions of, say, loss masses or something like that. But they were chosen without even knowing that the problem of computing the molecular formula of the precursor existed. And that's how you can do it. That's how you can be sure that the whole thing is not overfitting like hell. Now, how good does it work? This is now a comparison between the old scoring, which was chosen ad hoc, and the new scores, the posterior probabilities. And you see a dramatic increase here. But you also see the difference between 2 different algorithms. The DP algorithm, dynamic programming algorithm, that's the parameterized algorithm, as I told you, only considers the 10 or 12 most intense peaks and inserts everything else heuristically, whereas the integer linear programming, it considers all the peaks. And the really surprising thing is that you get 10% identification rate just by considering all the peaks, just by solving the problem exactly and not with such a crude heuristic. I mean, the DP is exact, but then on top of that, we reinserted peaks. You really have to make sure that heuristics do a good job. But anyways, from the SIRIUS 2 paper to the SIRIUS 3 paper, the improvement was more than twofold the number of correct molecular formulas. And if we now combine that with the new isotope patterns, then we were, with the old isotope scoring, at 80% correctly identified molecular formulas. Now we are getting close to 90% correct molecular formula identifications, or annotations, if you prefer that word. I assume that it's even a little bit more, because we are now in the region where it should actually quickly converge to 100% now, but it's not. It's stopping somewhere at 93%, 94%. And I assume that our reference data contains a few misannotated things. So where we believe it's this and that compound, but it's actually not, or where spectra were mixed up, or such things easily happen with humans, okay? Not only computers make errors, humans make a lot of errors. So I assume that it's even a little bit better than that. And now the usual question again, what about if I had really high mass accuracy data and I only use that and only use the monoisotopic peak to identify the molecular formula? How good would that work? This is now the comparison with 1 ppm data gets you less than 20% right. 100 ppb data would get you less than 60% right. And 10 ppb data, 10 parts per billion data, would still work worse than SIRIUS does with 10 ppm data. Okay? So high mass accuracy is very good, but you also still need a smart software that does something useful with it. Because if you would feed like 1 ppm data into SIRIUS, then the identification rates would go, probably beyond 90%, even for the top 1 position. Okay, so far we have only evaluated the molecular formula of the precursor, and we said it's a good fragmentation tree if the precursor molecular formula is right. And I told you that we don't have many chances for most of the data because we don't know a ground truth. It's really hard to evaluate that. Aleš Švátoš did that once for the analytical chemistry paper, and he literally went through hundreds of fragmentation trees, manually looking at each fragment, drawing the different possibilities, what could happen, and so on. But we sometimes said, yeah, this is possible. I don't know. It's possible, gas phase chemistry, this can happen. I can't say for sure. Luckily, we noticed that NIST contains long lists of molecular formula annotations for the fragment peaks. I mean, they give these spectra together with the structures to experts, and these experts, which are real experts, I mean, they have looked at literally trillions of these spectra for, I don't know, 40 years now. And they can then say, this is this molecular formula and this is this molecular formula. So we thought, let's compare to that. So now, how good are we for those molecular formulas? Assuming that we got the precursor molecular formula correct, otherwise, I mean, the experts know the structure. SIRIUS at least knows the precursor molecular formula. And then we see how good SIRIUS performs without any knowledge about the structure. And this is only an interim result, which I present here, but I thought the number is so cool that I have to show you. 99.5% agreement between the experts and SIRIUS. Even randomly choosing will get you somewhere like, I don't know, 50-60%, because sometimes there are not too many explanations. So we shouldn't say we got from 0 to 100%. It's more like from 50 or 60%. But this is nevertheless extremely cool, I think. Yeah, you will find a lot of fragments which are wrongly annotated, but a lot only if you look at a lot of fragmentation trees. Okay? Warning, spoiler alarm, this only works when we get the molecular formula right. If the root precursor molecular formula is wrong, everything in here is wrong as well. But that's trivial. Okay? That would be like giving the expert a wrong structure and saying, oh, you got everything wrong. This ends the SIRIUS part of my talk, and I come to the ZODIAC part, which is we still didn't stop thinking about molecular formulas. We are still not happy. We are not convinced that this is the end. And ZODIAC is, the brainchild of this being not totally satisfied with what SIRIUS is doing. And the point why we were never completely happy with SIRIUS performance is the higher the masses of the compounds get, the higher the error rate of molecular formula annotations gets. That's not really surprising. We do de novo. Okay, if you wouldn't do de novo for compounds around 800 Dalton, by the way, that would be really strange because the databases get fewer and fewer compounds for such high masses, so it would actually be easier to find the molecular formula, except that the current molecular formulas are a tiny subset of all molecular formulas, smaller and smaller. But for the more realistic problem, high masses, considering all molecular formulas, obviously it explodes. The number of molecular formulas explodes. It's not exponential, but it's a really nasty polynomial. And with that, it gets harder and harder to identify the correct molecular formula. Yeah, remember, where's Wally? Yeah, if we would zoom out 5 times now from the left where's Wally picture, you would have a really hard time finding him. And that has nothing to do with SIRIUS by the problem. It's simply the combinatorics of the whole problem. Yeah, nobody can prevent that. But now let's rethink this a little bit. When I told you a few minutes ago how SIRIUS selects the best molecular formula, then I told you for each molecular formula candidate, for the precursor, we compute the best fragmentation tree under this precursor and we score it. And then in the end, we use these scores to rank those candidates. And then we output the one with the highest score. But this information is not lost. We can use that. Okay, it's provided by SIRIUS. Why would we use that? Because we are usually not measuring one single metabolite. If you're doing something like that, there are applications where you are measuring single metabolites, okay, from pure substance or something, then ZODIAC is not for you, I have to tell you. This is really, the idea is that we have a complete LC-MS run, yeah. Some of these were selected and then MS was recorded. And we assume that there were, say, enzymatic reactions or other things that transform one metabolite, one compound structure into another one which is highly similar. And not all of them will be present, but some of them will be present. It's enough if a few things are present. We don't need everything. And the other thing that is known for a long, long time, and for example, GNPS molecular networks use that, but other approaches also use that, is if two fragments are very similar, not two fragments, two compounds share a similar structure, okay, then they also show a similar fragmentation behavior. The fragmentation spectra will look similar. That's why you can use the dot product to actually say that two unknown compounds might be structurally similar. For us, the important point is not only the fragmentation spectra are similar, these also have the same explanations, these peaks. This will be an H3PO4 in both of them, not just in one of them. So one explanation in one of them, another explanation in the other one of them. If this is the case, then also all the explanations of the fragments will be identical, or many explanations will be identical. The same holds true, by the way, for the root losses or precursor losses. Okay, everything that goes from here to there, but I'll leave that out. We use that, but I'll leave that out in the slides. It just makes things more complicated. And we use that to again create a network, but different from, say, the GNPS network, molecular networks, where we have such a network based on the fragmentation spectra. We now have such a network based on the fragmentation tree explanations of each fragmentation spectrum. And that's obviously much bigger. Yeah, for one fragmentation tree here and one fragmentation spectrum here and one fragmentation spectrum here, you have loads of different fragmentation trees here and loads of different fragmentation trees here. And now we compare any pair of fragmentation trees from the left and the right side and see how many fragment annotations they share, and see, by the way, also how many root loss annotations they share. And from that we compare a computer score. And if those two compounds are similar, then the correct fragmentation trees should share a lot of fragment annotations. I just showed you that. Whereas if you grab any two random and fragmentation trees here, the wrong one here and the wrong one here, or correct one here and an incorrect one here, they won't share too many fragment annotations. I mean, this is a completely more or less random tree, yeah, based on this data. It is wrong, so many fragments will also be wrong. So there will be a little bit similarity. Smaller peaks will also be explained as the same molecular formula, but there will also be a lot of differences. So our hope is that in these cases, the two correct fragmentation trees will get the highest score. And they will sometimes, and sometimes they won't. Okay, this is again statistics. You can't do anything against it. You can't be sure, just now grab the highest similarity here and assume it's correct. Actually, things will contradict each other. You will see if you now take yet another compound in this network, then something else will show up as the best scoring pair. And what we do now is we have a complete huge network. It contains 10,000 number of MS of these supernodes, but inside of them each fragmentation tree is now a true node, and then the fragmentation trees are connected to each other. That is about 500,000 of those fragmentation trees connected to each other. And inside of those, we now try to find a best assignment. So one of these fragmentation trees is correct for this molecular, fragmentation spectrum. That's the molecular formula of the compound. One is correct here, one is correct here, one is correct here, and so on. We combine both the initial SIRIUS score and the score that is derived from these edges. And these two things together then give us a total score. And unfortunately, if you now write that up, it's again an NP-hard problem. And this time it's really one where the NP hardness is for real. That means we can't give you the optimal solution, and I think it won't be possible in the future either at least for non-trivial instances. This has to do also with the size of the instance. As I said, that's 500,000 nodes, and that's 500,000 times a huge number of possible edges in there. What we use there is Gibbs sampling. Gibbs sampling now again is a statistical formulation. You write up how or define how for each assignment you think the posterior probability should look like, and then Gibbs sampling allows you to sample from that posterior distribution without ever having to really compute everything in detail. And with that you can then in the end even assign probabilities to each individual hypothesis here. Those are not only fragmentation trees, these are in particular different molecular formulas, and so that's how you find out which one is the correct and how sure you are about that. By the way, that's currently not that nicely working for ZODIAC. It has a problem that many of these approaches have. It's a winner takes it all problem. Usually it decides that one of these solutions has probability 1 and all others have probability 0, and this is not what we want. Nevertheless, Zodiac works quite nicely, and I've already shown you this slide, so here it is again. But we now concentrate only on Sirius and Zodiac because we know they are performing better than all other methods anyways. Now we can zoom in a little bit and we see, except for my stool, as I said, and those are horrible, horrible spectra. I am not even sure like how many of the ground truth spectra are actually not chimeric spectra. Except for that, it performs very, very nicely and roughly halves the error rate of Sirius. We are now usually well below 10%, and for some data sets even below 5%. Particularly interesting is the dendroids data set. Those are very, very large compounds, but somehow Zodiac really liked it. There were many similar compounds present, and so the networks were really rich, and so it decreased the error rate to, I don't know, something like 3%. But it gets even better if we tell the approaches what the correct adducts are. Sometimes we always take into account they can be protonated, they can be sodiated, and so on and so on. And if our software has to decide that itself, then these are the error rates. And if we tell our software what the correct adducts are, then error rate of Zodiac goes down to almost 0. I think this is a single wrong compound, molecular formula. Warning again, only complete LC-MS runs. And with that, I come to the end. I hope you found that interesting to learn a little bit about the background of Sirius, the two parts. One is the isotope pattern analysis, one is the fragmentation tree analysis. And our new tool, Zodiac, which can help you analyze complete LC-MS runs. Hopefully, it will become a little bit faster than it currently is. We have our ideas, and yeah, hopefully it will also become a little bit better, even better. Sirius is mature. There's not much more you can do. If the only thing that you have is an isotope pattern and MS, but for Zodiac, I have high hopes that it will actually be even better in 2 or 3 years. Here is a selection of a few people that contributed to Sirius and Zodiac, and that's definitely not complete. Many people are not on this list. So I'm very sorry to those. Like we started with this in Bielefeld, and Anton and my very, very smart student assistants are not on this list from Bielefeld. Florian Juja was the one who worked on the mass decomposition, and Sirius also. Florian more or less co-invented together with me the fragmentation trees that I presented you. I mean, everybody is free to use the words fragmentation trees, but the ones that I presented you were invented by him and me. Franzi and Kerstin further progressed with Sirius, and then Kai more or less rewrote everything with Sirius 3. That's the Sirius that everybody's using now, or Sirius 4. And Markus is responsible for Zodiac. And as I said, I probably missed a lot of important people here. I'm very sorry about that. I thank you very much for your attention, and if you found this interesting, you can now move on to the next talk, where I will talk solely about CSI finger ID, because if you thought this is complicated, then yeah, CSI finger ID will probably, yeah, it's mind-boggling. Anyways, many thanks for your attention. Bye.